Welcome to an application of multivariable calculus, moment of inertia for a solid cone. We will use triple integrals in spherical coordinates to find this moment of inertia. First, let's discuss the moment of inertia, which we will represent by the letter capital I. Suppose we have a rigid body having a mass m that is rotating about some axis A. So here's the mass, here's the axis A, which in this case happens to be an axis of symmetry, but it doesn't need to be. And this mass is rotating about this axis. We will define the moment of inertia I about that given axis of rotation A. Let's suppose this mass is rotating about that axis A with angular speed omega, and the resulting rotational kinetic energy is k sub r. We'll use this little subscript here to remind us that we're looking at the kinetic energy of rotation. So when this mass spins around this axis, all of the little pieces of this mass are moving with certain velocities. And if you have a mass moving with a certain velocity, we can define an energy associated with that motion. We would add up basically all of the kinetic energies for all of the particles making up this mass that are rotating around this axis. We will then say that the moment of inertia I is defined by this equation, that kinetic energy of this mass is going to be 1/2 I times omega squared. So we used omega to represent the angular speed. So what is this angular speed? What do we mean by this angular speed? Well, suppose that we have a mass that is revolving around some axis in a, let's say, circular orbit. Let's suppose the mass m, this mass right here, makes one complete revolution through 2 pi radians in an amount capital T seconds. Well, in that case, we have a periodic motion with period t seconds, and we will define the angular speed of this mass as the angular speed equals 2 pi measured in radians divided by t, which in this example we measured in seconds. So in this example I have measured omega in terms of radians per second. We'll almost always talk about radians when we're talking about omega, but of course t could be measured in seconds, hours, years, whatever. So what are the units of measure for this angular momentum I? Well, we have the equation which we used as the defining equation for I. The kinetic energy of rotation was 1/2 I omega squared. Well, the kinetic energy, which is energy, has the same units as an energy, let's say, measured as m times the velocity squared. And so that would be mass, and then velocity is distance divided by time. And since we have a square here, we have a square here. So what we could say is, if we have omega equal to 2 pi over t, where t is time, then omega has units 1 over time. I then has the units of the kinetic energy of rotation divided by 1/2 omega squared. The kinetic energy has units of mass times distance over time squared, and then omega has units of 1 over time squared. This is dimensional analysis, I guess you could say. We could be measuring mass in grams, we could be measuring distances in meters, we could be measuring time in seconds, for instance. But if you look at this, there's some cancellation going on. It can be simplified to mass times a distance squared. For instance, we could measure the angular momentum in units of kilograms, which is a mass, times meters squared, which is a distance squared. Let's talk about the rotational kinetic energy of a point mass revolving around an axis. Suppose we have a point mass m that revolves about an axis at a distance r with constant angular speed omega radians per second. So in time t seconds, the distance the mass m travels around this axis is going to be omega times r times that period of time t. The instantaneous speed of the mass around the axis then, actually I guess I should say the average speed, but we're also assuming that the speed doesn't change, so it is the instantaneous speed also. The instantaneous speed of the mass about the axis is the speed v equals the distance traveled by that mass divided by time, and the distance was r omega t, and time interval was t, and this simplifies to r times omega. So that's the instantaneous speed due to that rotation of the mass around this axis here. So the rotational kinetic energy of this mass about that axis is, the rotational kinetic energy k sub r is 1/2 mv squared, but the velocity, remember, was r omega. And so this simplifies to 1/2 m r squared omega squared. Here's a short example of these concepts. Suppose we have a mass of 2 kilograms that's revolving 3 meters from its axis of rotation at 5 times per second. Then we will have that omega is going to be 10 pi divided by seconds, 10 pi radians per second. Every second, this mass goes around the axis 5 times. 5 times 2 pi is 10 pi. So in that case, the kinetic energy given by 1/2 mr squared omega squared is going to be 1/2. The mass is 2 kilograms. The radius is 3 meters, and that's squared as we see here. And the value of omega, 10 pi per second, is also squared as we can see here. And if you multiply all these down and do the arithmetic, what you get is 900 pi square kilogram times meter squared per second squared. Now, if we think about it for a minute, kilogram times meter squared divided by second squared, this is a unit of energy which we called the joule. And so the kinetic energy of rotation is 900 pi square joules. Notice that we got a pi square here, and that was because we had an omega squared here, and omega happened to depend on pi. To find the kinetic energy of a cone rotating about its axis of symmetry with angular velocity omega, we will first partition the solid cone into subregions. For each subregion, we will find the volume of that subregion, find the mass of that subregion, find the distance r from the subregion to the axis of rotation. And if the cone is rotating with angular velocity omega, we will find its kinetic energy of that subregion, and then add up the kinetic energies of rotation for all of these small subregions to find the total kinetic energy of that rotating cone. When we follow this procedure, what we get will be a Riemann sum for a triple integral. We will use a triple integral in spherical coordinates to calculate the total kinetic energy of rotation of this cone. So we will focus on a solid cone that is rotating about its axis of symmetry. And we will set up an integral for the kinetic energy in terms of cylindrical coordinates, a triple integral in cylindrical coordinates. We will then use that to compute I. I will depend just on the geometry of the object, in this case a cone, and its mass. We will calculate the total kinetic energy due to rotation via an integral in spherical coordinates. So let's talk about spherical coordinates. Let's talk about the spherical coordinates of a point. Here is a representation of three-dimensional space. Here's the x-axis, y-axis, and a vertical z-axis. Pick a point out in space somewhere, and we want to define its spherical coordinates rho, phi, theta. And here's how we do it. First, notice that we do list rho first, phi, then theta. Rho is the distance from the origin out to that point here. So that's the first coordinate of this point, first of three coordinates. Then the angle phi. Phi is the angle between the positive z-axis and this line joining the origin to this point. So phi is this angle right here. What about theta? If we drop a perpendicular from this point down to the xy plane and then draw a, let's call it radius vector here, r, then theta is the angle between the positive x-axis and this line having length r. So theta basically is the same as the theta that you saw earlier in polar coordinates. So putting those three things together, rho, phi, theta, rho is this distance, phi is this angle, and theta is this angle. So rho is the distance from the origin out to the point whose coordinates we are concerned with. It's the distance from the origin to the point P. Theta is this angle down here in the xy plane. To get that, we drop a perpendicular from point P down to the xy plane, and then theta, after we draw this line r, this distance is going to be r. Once we draw this line, the angle theta is here, between the positive x-axis and this ray. This is the same theta that we saw in polar coordinates and also in cylindrical coordinates. Phi is the angle between the positive z-axis and this line that we drew from the origin to our point of interest. It's the angle between the positive z-axis and the line going from the origin to P. Let's talk about converting from rectangular to spherical coordinates. Suppose we have this point with spherical coordinates rho, phi, and theta, and we want to know the rectangular coordinates x, y, z of this point. Well, looking at a couple right triangles, we can easily see that rho squared equals x squared plus y squared plus z squared. Taking square roots, we would have rho is the square root of this stuff. If we look at the angle phi here, the sine of phi is what? Well, this angle right here is phi, and this angle right here is also phi. So the sine of phi is going to be r over rho. R over rho. R is just the square root of x squared plus y squared. Rho is the square root of x squared plus y squared plus z squared. Then what about the cosine of theta so that we can find theta? If we drop in the xy plane a line from this point right here, perpendicular down here to the x-axis. We have a right triangle here, and the tangent of theta is going to equal y over x, which is this formula right here. Also, if we wanted to use a different trig function, look at the cosine of this angle. It would be x over r, and in that case, r is the square root of x squared plus y squared. So we get that the cosine of theta is equal to x divided by the square root of x squared plus y squared. Let's see how we can convert from spherical to rectangular coordinates. Let's suppose that we have a point here in 3 space and its spherical coordinates are rho, phi, and theta. Well, in that case, let's see how we can write a formula for x, first of all. From rho, we drop a perpendicular to the xy plane, and from this point in the xy plane, let's drop a perpendicular to the x-axis. So that gives us a right triangle, a small one, right here. So if we look at this, we can see that x over the hypotenuse is equal to the cosine of this angle theta. So that tells us that x is equal to r times cosine theta. But what about r? If we look at this bigger right triangle over here, we can see that r has to equal rho sine phi. Since this angle right here is phi, this angle up here in this right triangle is also phi, and so we get that by looking at this large right triangle. R is rho sine phi, and so x is r times cosine theta, which is rho sine phi times cosine theta. The formulas for y are very similar. Looking at this small right triangle, instead of x equals r cosine theta, you'll have that y equals r sine theta. Now, once again, r is rho sine phi, so plug that in for the r right here, rho sine phi, and we have that y is rho sine phi sine theta. Also, by looking at this large right triangle with an angle phi right here, we can see that z is rho times cosine of phi. So these 3 formulas tell us how to go from rho, phi, and theta to x, y, and z. Here are 2 surfaces. The cone shown, the smaller cone, narrower cone, is phi equals pi over 6, and the wider cone here is phi equals pi over 4. Both of those, I think, go up to a radius rho of maybe 5. We can take a look at this to see what it looks like. So every point on this narrow cone has a spherical coordinate phi of pi over 6. Every point on this wider cone out here has a coordinate phi equals pi over 4. So these are surfaces of constant phi. If you let phi vary through everything from 0 to pi, you would get a whole sequence of cones that look similar to this. And every point in 3-dimensional space, except for the origin itself, would have a unique value of phi attached to it. These are the surfaces rho equals 3, an inside sphere, and rho equals 5, this outside sphere. We can rotate this around, and as you can see, it really is spherical. It's spherical about the symmetric about the origin. This is an example of constant surfaces of constant rho value. Rho equals 3 for this inside surface, rho equals 5 for the outside surface. Here is an illustration of two surfaces. One surface is rho equals pi over 6, and the other one is rho equals pi over 4. We can rotate this so that we can see a little bit more of it. To me, it looks something like a taco shell. This part is a plane, and this part also is a vertical plane. It looks like it's circular here because in SageMath I had to specify a range for rho and phi, and in this case I let rho go from 0 to 5. So we're getting for this surface points where the angle theta is pi over 6, and the rho value can go from 0 to 5. Phi, by the way, will go from 0 to pi in this diagram too. That's in the code that is above this figure. Let's talk about a spherical coordinate wedge. This is a diagram of one over here. This is the type of volume subelement that we will use in our Riemann sums when we integrate using spherical coordinates. This wedge, this three-dimensional volume, can be described as the points whose spherical coordinates satisfy rho is between rho naught and rho 1, phi is between phi naught and phi 1, and theta is between theta naught and theta 1. In this diagram over here, this side is going to be part of the surface rho equals rho naught, which in its entirety is going to be a sphere. The opposite side, which you can't see, but the back side here, is going to be rho equals rho sub 1. On the left and right, we have surfaces of constant values of theta. This surface, all the points have spherical coordinate where theta is equal to theta naught, and on this opposite side, which we can't quite see, theta will be theta sub 1. The top surface here is going to be a surface, all of whose points satisfy phi equals phi sub 1, and the bottom one, which once again we can't see, is going to be phi equals phi sub naught. So what happens is we're looking basically at, I guess you can say, 4 different surfaces, and parts of those surfaces in three-dimensional space are parts of this wedge. On each of these surfaces, we see one of the spherical coordinates is a constant. On this surface, theta is a constant, the number theta naught. On this surface here, all of the points satisfy rho equals rho naught, and so forth. In this particular illustration, this figure was generated using Sage Math, and the values of rho naught, rho sub 1, and so forth were these. Rho naught was 3, rho sub 1 was 3.5, theta naught was pi over 4, theta sub 1 was pi over 3, phi naught was pi over 6, and phi sub 1 was pi over 4. Here is another wedge from spherical coordinates where the difference in the radii rho is very small, the difference in phi values is very small, and the difference in theta values is very small. If you look at this, and we can rotate it around, this looks almost like a rectangular box. All the sides look like they're parallel, almost parallel at least, and intersect at right angles. Here's another representation of a small wedge in spherical coordinates. This one was generated using MATLAB to draw the edges of this wedge. If you look at this picture, here's the wedge obviously. This point right here is the origin of our three-dimensional space in rectangular coordinates, 0, 0, 0. The x-axis and the y-axis both have 0 here. If we look at this vertical z-axis over here, 0 is down here, which is right at the same level as these. So this point right here is 0, 0, 0. So coming off from the origin, this wedge is out here in some way, shape, or form, intuitively, let's say, facing that origin, where it has a certain length, width, and height. Let's consider the volume of a small wedge defined in spherical coordinates, where the sides, for instance, are of constant theta, constant rho, or constant phi. If the dimensions of the wedge are small, then the wedge is approximately a rectangular box, straight edges meeting at right angles. The smaller it is, the more rectangular it looks. And in this case, we can use the following approximation. For a rectangular box, the volume, which I'll call delta V for a small volume, is the length times the width times the height, delta L times delta W times delta H. We'll find out later that we will use this for our approximation in a Riemann sum for a triple integral, which we will evaluate in spherical coordinates. So what we need to do now is to find out how delta L, delta W, and delta H depend on the coordinates when you're working in spherical coordinates. In our calculation, we will be doing some approximations and simplifying the calculations by using the mean value theorem. You saw this back in Calculus 1, hopefully. Suppose you have a function f which is continuous on the closed interval ab and differentiable on the open interval ab. Then there is a number c in the open interval ab such that f prime of c, the first derivative of f at c, is equal to f of b minus f of a divided by b minus a. This equation can be written equivalently as f of b minus f of a equals f prime of c times b minus a. Here's a picture of the situation. This curve right here is y equals f of x. If we join a comma f of a, this point right here, with b comma f of b, which is right here, by a straight line segment, then there is some number c between a and b, such that if we look at f prime of c, remember, can be geometrically thought of as the slope of this f of x curve at c. So the slope of this curve right at c is equal to f of b minus f of a over b minus a which is the slope of this secant line. So this tangent will be parallel to this secant line. We now find the volume of a small wedge by finding its length, width, and height in terms of the spherical coordinates rho, phi, and theta, and also increments delta rho, delta phi, and delta theta. So let's first by finding the width of a small wedge. Here is our wedge. This face in front is part of the surface rho equals rho naught. So one of these vertices, this one, we'll call rho naught, theta naught, phi naught, theta 1, and the one over here we'll call rho naught, phi naught, theta naught. So that's the width that we're going to find. Also, we have a length of this small wedge we want to find, delta L, and also the height of this small wedge, delta H. But right now we will look at the width, this distance here. Well, if you think about it for a minute, the squared distance, delta W quantity squared, is the squared distance from this point to this point, which are given in spherical coordinates. So somehow we have to do some calculations to figure out what delta W is in terms of these spherical coordinates. So we'll start with delta W quantity squared being that squared distance, and x naught, y naught, z naught will be this point right here, and here it is written out in terms of transformation from rectangular to polar coordinates. X naught is rho naught sine phi naught cosine theta naught. Y naught is rho naught sine phi naught sine theta naught. And z naught is rho naught cosine theta naught. Similarly, this point here, if we write it out in rectangular coordinates, call it x1, y1, z1, it's going to be just about the same thing that we had up here. The only difference is all of the theta naughts are going to be replaced with theta 1s. So here we have a theta 1 instead of a theta naught. Here we have a theta 1 instead of this theta naught. And over here, nothing changes. So then we'll just use our distance formula in rectangular coordinates. The distance between those 2 points squared is the difference of these x coordinates squared, and if you subtract this and this, you notice that both of these have rho naught sine theta naught in it, and so they only differ right here. So this here minus this squared we can write as rho naught sine phi naught quantity squared times cosine theta 1 minus cosine theta naught quantity squared. So that comes from these first coordinates. Then subtract the y coordinates, this coordinate minus this coordinate, and once again there are some common factors in this and in this, and so when we take the difference of this and this quantity squared, we can write it as rho naught sine phi naught quantity squared times sine of theta 1 minus sine of theta naught quantity squared. Then we have the difference of the z coordinate squared. But this z coordinate is exactly the same as this z coordinate, so the difference is 0. So here we would add plus 0 squared. So we don't need that extra term. Now, let's remember from the mean value theorem that we could say cosine theta 1 minus cosine theta naught squared, quantity squared, over theta sub 1 minus theta sub naught quantity squared. That is going to equal minus sine squared of some angle, which I'll call theta star. Also, using the mean value theorem, we can say that this difference quotient, actually squared again, is equal to cosine squared of some other angle, theta double star. Theta star and theta double star are both somewhere between theta naught and theta 1. So what can we do then? Substitute these into here. And so the width squared, delta W quantity squared, is this stuff squared, which is right here. This stuff right here squared, we can write as minus sine theta star squared times theta 1 minus theta naught squared. Then for this next term, once again we have this factor right here, and then this stuff right here by the mean value theorem is equal to cosine squared theta double star times theta 1 minus theta naught squared. And if you look at this for a minute, you can see that we basically have here in this term a sine squared of theta star plus, right here, a cosine squared of theta double star. Well, if theta naught and theta 1 are close to each other, so very, very close, this is an itsy bitsy kind of semi-rectangular wedge here, then theta star and theta double star are just about equal. So sine squared of theta star plus cosine squared of theta double star is 1. And so what you then get after that simplification is you get this factor times, well, you have to look at both of these at the same time, I guess. You're going to have a factor of theta rho naught sine phi naught squared, and then you're going to have sine squared of an angle plus cosine squared of almost the same angle, and that's 1. And then you have a common factor of theta 1 minus theta naught squared. So all of this stuff simplifies to an approximation of rho naught sine phi naught squared times theta 1 minus theta naught squared. That was quite a lot, wasn't it? So then, once again, we have this equals this stuff right here. And we want to find delta W, this width up here. So just take square roots of both sides, and we get that width delta W is rho naught sine phi naught times, and then I'll call this difference, theta 1 minus theta naught, I'll call that delta theta, and that had a square here, but we're taking square roots, remember, so we just got a delta theta here. Square root of this factor is rho naught sine phi naught. Square root of this factor is just delta theta. So now we want to find the length of this small wedge, delta L. So that's the more or less approximately, to a good approximation for a very small wedge, this length right here, which is going to be the distance from the point rho naught phi naught theta naught and the point rho 1 theta naught phi naught theta naught. Notice that for this side right here, we have a common angle, theta equals theta naught, and phi equals phi naught also. But going from here to here, that radius vector length changes from rho naught to rho 1. So to find delta L, we need to find the distance between these 2 points. As before, we'll start by basically using the Pythagorean theorem again, but we'll look at delta L squared. So let's see how we can do that. First of all, we'll say that delta L squared is the square distance between this point down here and this point up here. X naught, Y naught, Z naught is rho naught sine phi naught cosine theta naught, rho naught sine phi naught sine theta naught, rho naught cosine of phi naught. And the other point up here, rho 1 sine phi naught cosine theta naught, rho 1 sine theta naught sine phi naught sine theta naught, and rho 1 cosine phi naught. So let's take the difference of these x coordinates, quantity squared, plus the difference of these y coordinates, quantity squared, plus the difference of these z coordinates, quantity squared. This time the z coordinates are not equal. Here we have a rho naught, here we have a rho 1, so that third term is not 0 anymore. It's this stuff right here. So now we'll play the same sort of game that we did before. First of all, we notice that we have a rho sub 1 minus rho naught squared times this. And where did that come from? Well, let's see. We have a rho 1 sine theta naught cosine theta naught here, and we also have somewhere else, I guess right here, the same sine and cosine factors that we have here. So basically we factored out what? Rho 1 minus rho naught from this. We factored out the product of the sine and cosine from each of these, and then we squared it. So that's basically where this came from. If we look at this one, we have something similar. You have sine phi naught sine theta naught. You also minus here sine phi naught sine theta naught here, and this difference is squared. And so just doing a little bit of algebra once again, factoring out that common sine times sine here, we get rho 1 minus rho naught squared times sine phi naught sine theta naught squared. And then over here, this has cosine phi naught, this also has cosine phi naught, so this squared term we can write as rho 1 minus rho naught squared times cosine phi naught squared. Well, so we made a little bit of progress by just factoring out some things. So now let's see what we had here. We have, I guess, some combining of terms, don't we? We have rho 1 minus rho naught squared, which is this stuff right here. We also have a sine of phi naught, which is squared, which is right here. And then, if you look in this next term, we have this same factor. We still have that sine of phi naught. And so the only difference is this cosine and sine of phi naughts here, isn't it? And so what we're going to get in that case is, well, this factor times this factor, which we just saw, times cosine squared theta naught plus sine squared theta naught. Okay, and so this stuff right here is a simplification of these two terms. We also have this third term here, and I'm basically going to leave that the way that it was. So let's see what we have here. The length squared again is this factor squared times this factor squared plus, and then, well, first of all, before we do that, look at what we have here. Cosine square theta naught plus sine square theta naught, that's equal to 1, isn't it? So that means that we have this squared times 1. And so that's this stuff right here. So this stuff right here is equal to this stuff right here. Plus, and then what happens here? We have rho 1 minus rho naught squared cosine phi naught squared. We just wrote it down again, didn't we? And then if you look at this, what do we have? Well, we have a common factor in this term and in this term of rho 1 minus rho naught squared. So we factor that out, and then we have that stuff squared here times sine squared of this angle plus cosine squared of this angle. And so that's what we have right here. Well, when you look at this, sine squared theta phi naught plus cosine squared phi naught, that's just 1 again, isn't it? And so this just simplifies to this square times sine squared of phi naught plus this thing squared times cosine squared of phi naught, as we had here. This, I already told you, is equal to 1. And so this times 1 just gives us rho sub 1 minus rho sub naught squared. So the length squared is this. Take square roots of both sides, and we have the length that we have up here in this wedge is a very good approximation, rho 1 minus rho naught. And for rho 1 minus rho naught, let's just call that delta rho, the change in the rho value going from this point up to this point. So now we have a very nice, very simple formula for the length of that side of this wedge. So now we need to find the height of that small wedge. The height, delta h, is this length right here in this almost rectangular wedge. Remember that we're looking at a very small wedge here, very small values of the length, width, and height. Well, for the height, that's going to be the distance from this point up to this point here. If you think about it for a second, rho is the same for these 2 points, and it's equal to rho 1. The elevation angle changes, though, from phi naught to phi 1, and that's reflected in the second component. And the theta value doesn't change, so they'll both be, let's say, theta naught. So we want to find this distance squared. So delta h squared is the squared distance between this point and this point, which is what we wrote right here. These are the corresponding rectangular coordinates of that point. This stuff is x naught, this stuff is y naught, this stuff is z naught, and down here, this stuff is x sub 1, this stuff is x sub 2, this stuff is x sub 3. So we're going to look at the difference of these first coordinates quantity squared plus the difference of these second coordinates quantity squared plus the difference of these third coordinates quantity squared, and that is what we have written out here in gory detail. So what we need to do is to simplify that, and simplify, simplify, simplify. So this is going to require doing some algebra and perhaps using some trig identities along the way. So we have delta h squared equals what? If we look at this first term here and compare it to what we have up here, notice that inside this square we have 2 terms, each has a rho 1, and each of them has a cosine theta naught. So we can factor that out and get rho 1 cosine theta naught quantity squared times sine phi 1 minus sine phi naught, also quantity squared. If we move on to the next term right here, about the same sort of thing happens. We can factor a rho 1 out of each of these terms. We can also factor a sine theta naught out of each of these terms. And so this stuff squared equals rho 1 sine theta naught quantity squared times sine of phi 1 minus sine of phi naught. This sine of phi 1 minus this sine of phi naught. In this last term, all we can do is factor out a rho 1 squared. If we now look at this a little bit further, we see that we have this term this factor in this term. We have also a rho 1 sine phi naught squared in this term. Both of these terms have the sine of phi 1 minus sine of phi naught quantity squared in there. So factoring that, we get the height squared is rho 1 cosine theta naught quantity squared plus rho 1 sine theta naught quantity squared times sine of phi 1 minus sine of phi naught squared. And then this term, we'll do nothing with it yet. So now what can we do? We notice that here we have rho 1 squared times cosine squared theta naught plus sine squared theta 1. So that stuff right here just simplifies to rho 1 squared, and then we have this second factor. This second term is just the same as what we have up here. So we had that delta H quantity squared is rho 1 squared sine phi 1 minus sine phi naught quantity squared plus rho 1 squared cosine phi 1 minus cosine phi naught quantity squared. Now, we can write this part right here and this part right here by the mean value theorem as what? If we divide this squared by phi 1 minus phi naught squared, if we divide this stuff squared by phi 1 minus phi naught squared, and then multiply by phi 1 minus phi naught squared on the outside, we can see that these are, what we have up here is equal to what we have down here. And by the mean value theorem then, sine phi 1 minus sine phi naught over phi 1 minus phi naught, that's equal to cosine phi star for some phi star between phi naught and phi 1. Similarly, this fraction in here is equal to sine phi double star for some double star between phi naught and phi 1. And they're both squared, so we do have squares there. And then it's times this difference squared. So that tells us then that delta H squared is equal to this plus this times that. Looks like I just copied stuff down again, I guess. Not much difference there. But let me just point out at this stage that phi star and phi double star are somewhere between phi naught and phi 1. And as this rectangular box gets smaller and smaller, phi 1 and phi naught are going to get closer and closer to each other. These phi stars and double stars being sandwiched between these two numbers also get very close to each other. So for very small boxes, these two angles are just about the same. And if they were the same, cosine squared of this plus sine squared of this would equal 1. So in approximation for very small boxes, we can say that that is essentially equal to 1. And we can replace that with this factor of 1. Phi 1 star, the common factor here, rho 1, I should have said, rho sub 1 squared, times 1 times this different squared. And then we can write that as rho 1 times delta phi. Or I call, well, yeah, rho 1 times delta phi. So we have that the volume of that small wedge, which is almost a rectangular box, is the length times the width times its height. And we saw then through the previous calculation that delta V is the length, which is delta rho, times the width, which is rho sine phi d theta, times delta H, which was rho d phi. Delta phi. So basically what we have is the volume is rho square times sine phi delta rho times delta theta times delta phi. So for small boxes, this gives us the volume of it, that small box-like wedge, in terms of the angles rho phi theta and also delta rho, delta theta, and delta phi. So when we do integration by looking at Riemann sums, what we will do is when we need the differential of volume, it will be rho square sine phi d rho d theta d phi. So we want to calculate now the moment of inertia for our solid cone. So let's assume that the cone has height h and radius r and has a mass density of delta. We'll assume that this cone has a uniform mass density. Well, in that case, the mass of the little element that we have up here, the mass of the entire cone is going to be the volume of the cone times the mass density, which is 1/3 pi r squared h times that density delta. So we'll consider a volume element, maybe this one right here, the wedge. It's a set of rho, phi, theta, a set of points having those spherical coordinates, such that rho is between rho sub j minus 1 and rho sub j, phi is between phi sub k minus 1 and phi sub k, theta is between theta sub m sub minus m minus 1 and theta sub m. And we'll assume that that has volume delta v sub jkm, and its mass is delta m sub jkm. So we're using this v for the element itself, that geometric thing that we see up here. Its volume of that wedge has a delta in front of it. The mass has a delta in front of it too. Okay, so what we then need to do is say, well, for this one wedge up here, the kinetic energy of rotation is equal to 1/2 the mass of that wedge times the radius out to that wedge times omega squared. But the mass, remember, is delta times the volume of that wedge, and so the kinetic energy can be written this way: 1/2 delta times delta v sub jkm r sub j squared times omega squared. Now, we have a whole bunch of wedges filling up this whole cone. No extra spaces left over, hopefully. If we have some space left over, we want it to be very small, and in the limit, let that unaccounted for empty space go to 0. So the total kinetic energy then, K sub r, is the sum over J, K, and M of these kinetic energies of these wedges. We're adding up the kinetic energy of all those wedges, and we get an approximation to the total rotational kinetic energy of that cone. Well, if we look at this, we notice that it is a Riemann sum for this triple integral. The triple integral over the cone, 1/2 delta r squared omega squared dv. And what we then have to do is figure out how do we write this triple integral over that cone using spherical coordinates. So we need to describe a cone in spherical coordinates so that we can set up our triple integral. So let's suppose that we have a cone. The vertex is at the origin. This is the z-axis, vertical. The radius of this cone is r, and the height of the cone from this vertex up here, that distance is h. Let's let phi just be an angle between the z-axis and some point. So the first thing we can say is that theta has to be between 0 and 2 pi. Theta can be anywhere basically in the circular region. If a point is at the top of the cone, then the z-coordinate of that point has to be equal to h. But the z-coordinate of a point in spherical coordinates is rho cosine phi, so that has to equal h. So solving this for rho, we have that rho is equal to h secant of phi. So to be inside the cone, we have to have rho somewhere between 0 and h secant of phi. So once we have an angle phi here, then rho has to be somewhere between 0, which will give us the vertex, or up to the top of this, which is h secant of phi. To see that, you can just look at this right triangle and get it from there. So the largest phi possible, let's call it phi max, is going to be given by the equation tangent of phi max equals r over h. That occurs when you're looking at a point at the top of the cone right at the edge here. So solving this, we get that phi has to be somewhere between 0 and the inverse tangent of r over h. Because phi can be over here, or it can be all the way over here. If we have a point on the z-axis, phi is 0. If we have a point right on this edge of the cone, then phi is going to be inverse tangent of r over h, because the phi value for a point right here is the same as the phi value for a point right here. And if you look at this point, then you have a right triangle with sides r, h, and a hypotenuse going up to here. So what we get then for the description of a solid cone is the following. The cone in spherical coordinates is a set of points with spherical coordinates r, theta, and phi, such that, rho, theta, and phi, such that rho is between 0 and h, secant phi. Phi is between 0 and the inverse tangent of r over h, and theta has to be between 0 and 2 pi. It's between 0 and 2 pi because we're looking at the full cone all the way around the z-axis. So any value of theta between 0 and 2 pi corresponds to a possible point in this cone. So let's remember we're letting delta be the mass density of the cone, and the cone has uniform density. I tend to use rho for mass density, but in this case we're using the Greek letter rho as one of the coordinates in spherical coordinates. So the entire kinetic energy of rotation of that cone is the integral over that cone of 1/2 the density times r squared times omega squared, the angular speed, dv. Now, when we set up the triple integral as an iterated integral, we're going to let theta go from 0 to 2 pi. We're going to let phi go from 0 to the maximum value that phi can have, and we'll let rho go from 0 to the maximum value that rho can have, and then the integrand is r squared rho squared sine phi d rho d phi d theta. Let's remember what's happening here. First of all, r here is squared, and we have it here. The omega squared is right here. The delta we have is here. The factor of 1/2 is here. And for dv, dv was rho squared sine phi d rho d phi d theta. So this was the transformation we had from volumes, I guess, in rectangular coordinates to volumes in spherical coordinates. So we know that phi max is inverse tangent of r over h. We also know that rho max is h secant phi, and so we'll just plug these two upper limits into those integrals down here. So we now have the entire total kinetic energy of rotation of that cone, that solid cone, is given by this integral. So when we evaluate this iterated integral, we'll first be integrating with respect to rho, where rho goes from 0 to secant h secant phi. After we calculate this inside integral, the next thing we'll do is integrate whatever that was with respect to phi, where phi goes from 0 to inverse tangent of this stuff. And once we've evaluated that, we then will integrate with respect to theta, where theta goes from 0 to 2 pi. And let's see what's happening here. This first integral, the innermost integral, has an upper limit that depends on phi. The second to last, or second to first, second to the innermost integral, I guess we can say, goes from phi equals 0 to inverse tangent of r over h. In general, this upper limit could involve theta also, but in this case it didn't for a cone. And then we just have on the outside integral, theta goes from 0 to 2 pi. Whenever you're setting up one of these iterated integrals in spherical coordinates, the outside, the most exterior integral will have constant limits of integration. It might not always be theta, but this outside integral, the outermost integral, will have constant limits there. I guess there are some cases where you could have non-constant ones here if you don't have a geometric figure that's fixed in its dimensions. You could be looking at a region that varies with time, I guess. So maybe that would change things here. But in any case, in this case and in most cases, we'll have this sort of situation happening. So we have the kinetic energy of rotation of that cone is 1/2 this iterated integral r square delta omega square dv. And we saw before that we could pull out the 1/2 delta omega square because those are basically constants as far as this integral is concerned. So here's the triple integral, and we're integrating r squared delta, well, the omega squared and the delta were already pulled out here. So r square, and this should be rho square sine phi d rho d phi d theta. Now, we don't use r in spherical coordinates. We used it as one of the coordinates when we looked at cylindrical coordinates. And there's a relationship between the two. If you look at the z-axis coming straight up, and you have this angle phi coming out like this, so the angle phi is here. And if we're looking at a point up here that has the coordinate rho in spherical coordinates, then the distance here is going to be r, the distance to the z-axis, the axis which we're rotating about. And looking at this right triangle, we can see that r is equal to rho sine phi. And so, plugging that in for the r squared here, this integral is the same as the one we have up here, except r squared is rho sine phi quantity squared. So let's evaluate the triple integral that we have here, which was involved in the calculation of the kinetic energy of this rotating cone. We will use Sage Math to evaluate that triple integral. So we start with the inside integral. The integral rho goes from 0 to h secant phi of rho sine phi quantity squared times rho squared sine phi d rho. So that integral is right here. If we use Sage Math to evaluate it, we do that actually in step 2 here, cell number 2 in the Sage Math notebook, a Jupyter notebook. I'll let A1 equal, and then we'll integrate as what we saw a minute ago, rho sine phi quantity squared times rho squared times sine phi, and we're integrating it where rho goes from 0 to h secant of phi. And then after the evaluation of that, we show what I1 was. I1 turned out to be 1/5 h to the 5th secant of phi quantity to the 5th sine of phi quantity to the 3rd power. So we can write that as 1/5 h to the 5th secant to the 5th of phi sine cubed of phi. Then after that, we need to evaluate the integral where phi goes from 0 to this inverse tangent of r over h of this integral, which we just figured out right here. And so that's in step 4 here. We're going to have I2 equals basically the integral of 1/5 h to the 5th times secant of phi raised to the 5th power times sine of phi raised to the 3rd power, integrated with respect to phi, going from 0 to the arctangent of r over h. When this is evaluated, the integral is equal to this stuff right here, which looks very complicated. Well, this simplifies quite a bit just using some algebra, and if we take this, which is called I2, and we do a full simplification of I2, all of this stuff just turns out to be 1/20th times h times r raised to the 4th power, which we can show in normal mathematical notation this way, 1/20th h times r to the 4th. So that gives us this integral equals 1/20th hr to the 4th. So what we have evaluated so far is this double integral over phi and rho, and we still need to integrate with respect to theta going from 0 to 2 pi. Well, we notice that there are no thetas in here, and so what happens is integrating that with respect to theta, where theta goes from 0 to 2 pi, just gives us an extra factor of 2 pi, which I don't show that part of the calculation here. It would just be easy. This integral up here, this iterated integral representing our triple integral, would just be 2 pi times this, which is 2 pi times this stuff right here. To complete the evaluation of our iterated integral, we now have to evaluate the last integral, the outside integral, the integral from 0 to 2 pi, 1/20th hr to the 4th d theta. This doesn't depend on theta at all, so our integral is just 2 pi times this stuff, and that simplifies to pi over 10 hr to the 4th. So that tells us then that the rotational kinetic energy is 1/2 the mass density times the angular speed squared times that integral that we just evaluated. And we know the value of this integral. We just found it up here by sage math. So the rotational kinetic energy equals this factor, which is right here, times this iterated integral, and its value is right here. So now it's time to find the moment of inertia I. So far we have that the kinetic energy of rotation for that cone is equal to this, but let's remember that we know something about delta here. Delta is going to be the mass of the cone divided by the volume of the cone. Let's recall that we're assuming that the cone has a uniform mass density. Well, the volume of a cone, you learned in geometry some time ago, I guess, 1/3 pi r squared h. So this fraction simplifies to 3m over pi r squared h. So we're going to substitute this value for delta into the formula up here for that kinetic energy of rotation. So the kinetic energy of rotation then is 1/2, and then delta is this stuff here, and then omega squared, which is right here, times this factor, which is right here. This is easy to simplify. I'll let you do it in your spare time if you want to, but this times this turns out to be 3m r squared over 20 times omega squared. You can see that this is an easy simplification. We have r to the 4th divided by r squared, which gives us an r squared here, and so forth. We have h divided by h, which leaves no h in this formula, and so on. But let's remember also that we know that the rotational kinetic energy by our definition of the moment of inertia is equal to 1/2 I omega squared. So the kinetic energy that we calculated up here also has to equal I omega squared. And this equation right here we can easily solve for I. Multiply both sides of the equation by 2, divide both sides of the equation by omega squared, and what we get is that the moment of inertia is 3/10 mr squared. This is the same result that we got when we solved this cone problem using cylindrical coordinates. So it should not be a surprise. We were solving the same problem twice, once with cylindrical coordinates in a previous video, and this time in spherical coordinates. So what did we do? We discussed spherical coordinates and saw how to transform from rectangular coordinates to spherical and vice versa, from spherical to rectangular coordinates. We discussed the concept of the moment of inertia and how it is approximated via Riemann sums. We used this to set up a triple integral for the total kinetic energy of rotation of this cone around its axis of symmetry. We wrote the triple integral as an iterated integral. We evaluated the iterated integral using sage math to find the exact value of k sub r, the rotational kinetic energy. The triple integral, the iterated integral for the triple integral is actually kind of messy to evaluate if you do it by hand, so we decided to use sage math in this particular case. And finally, we use the fact that the kinetic energy of rotation is equal to 1/2 I omega squared to find I. I hope that you enjoyed this video. Please stay tuned for more videos in the future.